see my screen now?
Thank you, Victoria.
Yes, we can.
Okay, cool. Thank you. Okay, so I'm going to start with just giving a few definitions in layman's terms, so like not to scare anyone off on machine learning. And they'll be a bit simplistic in nature, but if you're very interested in the topic, you can delve into all the nuances of machine learning. There are plenty online, there are plenty of free resources to learn about this very interesting topic. So I'm going to start off with what is machine learning. So machine learning simply is the automated detection of meaningful patterns in data. So in our context, the data we'll be talking about is Earth observation data, and more specifically, this will be Sentinel-1 satellite imagery. A good example for us of machine learning on satellite imagery is is the use of it in land cover classification. And one of the data sets we have in the DE Africa platform, or specifically the sandbox, is the ESRI 2020 Global Land Use Land Cover Map. Now, this data set was produced by applying a deep learning model, which is a machine learning algorithm on multiple Sentinel-2 scenes across the year 2020. You can, for more details on this data set, you can see the link that I've placed here. And it has this little write-up has also links to the product manual and algorithm document of how the ESRI 2020 land use land cover map was produced, if you want to go into all the details on it. Now, the most common way we categorize machine learning algorithms is by saying whether they are supervised or unsupervised. Now, you can go into the other ways you can categorize, but this is the simplest way we can go about it. So we have the supervised machine learning algorithms, which extract data from known examples and use the insight they've gained to engineer repeatable outcome. These known examples are the training data used to train the algorithm. Let's think about it this way. In terms of the human brain being a machine, when you're growing up, probably someone first time, you may not remember, but the first time you saw a cat, someone told you this is what a cat is. If you only had that one point of reference, and let's say it was a brown cat, if you saw a black cat, you wouldn't really say that it's a cat. You'll ask again, is this also a cat? Now, as you continue to grow older and someone showed you a brown cat is also a cat, and another black and white cat is also a cat, your brain sort of made those inferences that these are the unique characteristics of a cat. So if you see, let's say, you've never seen before that tiger striped cat, you'd probably look at it with all this reference information in your brain and go, yes, this fits the categories of what I think a cat is. So in your mind, you'll say, this is a cat. Now, even if you saw a dog at this point and you don't know what a dog is, you'll say, I know this is not a cat. I may not know what it is, but I know it is not a cat. So that's how supervised machine learning algorithms work. You give it training data so it knows this is what I am looking for, or the characteristics I'm looking for in this data, and then it's able to make categories from that. Now bring it back to our case of land cover classification. You're feeding your model training data and you're telling it, this is the characteristics when you're looking at, let's say, NDVI pixel values, that this is what vegetation should look like, or this is what urban areas or the built land cover class should look like. So after you train the model and apply it on your data, it's able to make those classifications using the insights it's gained from the data. Now, moving to the second category, this is unsupervised machine learning algorithms. Now, unsupervised machine learning algorithms are simply the opposite of what supervised is. These algorithms find hidden patterns in data by finding the similarities and differences in data without having been trained using training data before. So now again, we go back to my example of the human brain. If you encountered an image such as this, and you absolutely don't know what these are, your first probably instinct, if you're told to group this data or categorize this data, is probably go by color. So you try separate out all these diverse objects based on the characteristic you think will give you a better idea of what are the similarities in this data and what are the differences in this data. So that is basically what unsupervised machine learning algorithms do. Now bring it back to the case of land use land cover classification. If you give, let's say, again, your model NDVI of a certain area, it will try to create groupings or clusters from the data by finding, okay, what is this characteristics that gives me, best allow me to put similar items together and also allow me to have separate groups of these items at the same time. Now, the algorithm that we used in the urban area mapping for Sentinel-1 is the k-means clustering algorithm, which is now an unsupervised classification or machine learning algorithm. So that means there is no training data involved when we're trying to group to get our land cover classes. And our land cover class, the main class we'll be working with is built up or urban areas and non-built up or urban areas. So for the k-means clustering, how it basically works is it splits data into k number of distinct and non-overlapping clusters. And with this k, and this k is the number of clusters you wish to create. So you'll see in the algorithm, you'll define, I want 2 clusters or 2 groupings or 3 clusters. Those are 3 groupings and so on and so forth. So what the k-means clustering algorithm will do is it will assign each, I'd say, each pixel in your image to exactly one of the clusters that you've made available to it. So the next section we'll be revisiting, just to give us as we go into the notebook, is after we've done our classification, we usually want to validate our results. And what happens in validation is we are trying to compare, okay, this is the output from the model. How does it compare with ground truth data? So that we know how well the algorithm performed. So ground truth data is the factual data that we've gathered from the real world. And accuracy metrics are how we report how well the validation has gone. So you'll encounter metrics like overall accuracy or producers accuracy or users accuracy. So those accuracy metrics are just telling us, okay, when we compared our output from the model and what we took as the ground truth data, this is how well our model has performed. So now we'll go into the actual notebook. Are there any questions so far before we go into the example? Okay, if there are no questions, we'll move on to the exam, to the
I think it's so clear.
Mhm. Okay, good. So now we'll move into the notebook. And so the case for radar data in this case is, yes, we can use optical data to classify urban areas. It has been done with, like, again, the example I gave was the every land cover or any other land cover land use data set that is available to us. However, optical data tends to be limited in that it's affected by weather conditions such as cloud cover, which could be quite a severe limitation, especially in tropical areas like parts of Africa, especially around the equator. So radar data overcomes these limitations in that it's not dependent on the light from the sun. So this makes it able to acquire data even during the nighttime, or even when there's heavy rain or heavy cloud cover over an area. So I'm just going to restart this notebook just so we have a clean area we're starting from. Okay. So at this point, I'm just running the initial, what we usually do for every other notebook, the loading the necessary Python packages, creating a task cluster. There is a notebook in the, I think it's in the beginners folder, where if you want to know more about how to work with task, you can use that notebook as reference. So we one here, and then we define our area of interest. This area of interest we have here is Nairobi, the county of Nairobi in Kenya. Here we have it. Then we load the Sentinel-1 data. For the Sentinel-1 data, since we tried to keep it only to the for the first 4 months of the 2020 year. So that range of dates is good enough to give us a good chunk of data that we can work with, and without and that accounts for seasonal variations. We also convert the digital number values. That's the original, I would say, the value type that the Sentinel-1 data comes in into the decibel values. And as you can see in the cell, we do this because when using Sentinel-1 for analysis, the backscatter in the decibels unit has a more symmetric noise profile and is less skewed. So it's much easier to use for statistical evaluation than using the digital numbers. One of the underlying principles for this notebook was, as we can see here, if you've seen the picture of Nairobi before, you can tell that urban areas tend to have a higher backscatter value in Sentinel-1 than other land cover classes, which makes it easier for us to use the k-means clustering when trying to get the land cover class from to differentiate it from other land cover classes. In the next step, we'll not be using each individual image from the Sentinel-1 dataset we loaded. However, we'll be using a median composite of the images, which works better for machine learning and other analysis procedures that we do. Yeah, and we'll run it here. And these functions here just to help us run the k-means clustering for different clusters, sets of clusters. So like in this cell, we've specified we want to see what's the result for when we use 2 clusters or 2 groupings, or we use 3 or 4 clusters. Right. Now, as you can see here, when we use two clusters, these are the two groupings that the algorithm gives us. When we use three clusters, these are the groupings that we're given, and we use four clusters. Now, when I compared this with how other land cover maps produce show building areas, you can see that using three clusters gives us a better result than using either two clusters or four clusters for the area. So we can now decide which model and which class to assign as urban. So we use these results here are given in form of a dictionary. So we pick, okay, the best results is using three classes, and which pixel value here is the one we think shows the urban area or built land cover class better. So in this case, it will be the 1, because you can see here it's covered quite well. Yes, and as you can see here, now we'll validate what we've done using the ESA world cover product. So this is what we'll take as our ground truth, and we'll load it here. And then we'll plot the two side by side so we can see what happens. So this is a ESA world cover, and the yellow pixels are what has been classified as the urban or built land cover class. And as you can see from our k-means clustering model, it did a pretty good approximation. It's not as detailed like as you see here, the roads covered, but it's done a pretty good job. And we can report on this accuracy using the accuracy metrics here that we'll use the overall accuracy, producer's accuracy, user's accuracy, and the F1 score. So we'll print them out here. And we can see the overall accuracy was 79%, which is not the best, but it's done pretty well for it, pretty well considering there is no training data involved. And we can also have a visual image of how this performed. So these are the blue areas are what the algorithm produced as false positives, which it said it classified these areas as urban areas, but in the ESA world cover, which is what we're considering our ground truth, these are not urban areas. These are in short, the non-urban area classes areas. The red is the false negative. These are areas that our clustering classified as non-urban areas, but in our ground truth, these are urban areas. And then the true positive areas, as we can see in this white areas around, these are where both the clustering and the ground truth agreed that these are actually urban areas. So this is the end of our first example. Before we run another example for a different area, are there any questions?
I have a question.
Yes.
Yes, for the ground truthing. So, did you also go to the ground to do some?
Please, we don't hear the question.
Hello?
Please be close to your camera, to your microphone. I don't hear anything about what you are saying.
I think
Please.
let me remove the microphone. The earphones. Hello?
Yes.
Can you hear me now?
Yes.
Okay,
Yes.
I was saying, I want to know if you did any ground truthing or you just use the land cover from Esri, like you said, or do you find it necessary that someone should actually go and do the the groundwork for themselves?
In this case, for the ground truth, I used the ESA world cover land dataset as what will be our ground truth to compare the results of our algorithm. So if you were doing, let's say, a production, this was a test. If you're doing, let's say, a production for a real area, it is advised to create your own ground truth dataset if it's really necessary.
So I just want to confirm. So you mean this will be the, I don't know if the ESA, the European Space Agency data set was ground truth, or they also used unsupervised classification. So that's what I'm saying. In any case, does it mean we are all set? We can just use the ESA as our validation land cover, the land cover from ESA as a sort of ground truthing for our work.
Yes, you could use like in this case, I used the ESA as the ground truth. So because I was running the classification for 2020, as you can see up here in the time I picked for the Sentinel-1 imagery, and the ESA world cover was produced in 2020. So I used that as, I figured that was good ground truth data to use to validate the results. You can use it. I hope that answered your question.
No, it's fine. You can continue.
Okay.
Thank you so much, Victoria. I hope it's not sounding like a PhD defense. This is simply preliminary results, and everyone's contribution is just a comment, and we are here to work together. Thank you so much.
Hi, Ken.
Yes, my professor.
How are you, sir? And how is everybody?
Everybody's well.
Okay. I missed out a bit on Victoria's presentation. By the way, it's a very interesting presentation and analysis. I was just going to ask about the accuracy measures that were used. I saw overall accuracy, I saw user and producer accuracy. I want to find out if she went ahead to do some like kappa statistics in this work.
Oh, no, I did not use the kappa statistics for accuracy measurement, but you can add it from the function is available in the sklearn packages, so you can add it in.
Okay, Victoria, that would be very interesting to look at, because kappa basically gives you the results that is out of chance. I mean, so it takes out chance from your results. So then whatever readings or values you get for kappa, it gives you a true reflection of your accuracy. So it'll be interesting to add kappa to see how that plays out.
Cool. Yeah.
So thank you, Benjamin, for the interjection. Please, Victoria, continue with another example as we digest this amazing work.
I was actually about to call, does anyone have another area that would like to run this to test out this algorithm, the k-means clustering?
Yeah, we can do Accra, Ghana.
Okay. Do you have the coordinates for the area?
Yeah, sure. Give me a second. Let me pull that out. One second. Okay, so let's look at latitude 5.644626.
Oh, please put it in the chat.
Or I should type it into the
Yeah.
Oh yeah, let me drop it in the chat now. Yeah. Oh, someone just posted it, right?
Just for you, my professor, it's here.
Okay, so I mean that's fine. Yeah, Ken just did that. So Victoria, you can go ahead and use that.
The 5 points is a latitude. Ken?
That's correct. Lat long.
Okay. Okay. Copy function's not working.
So maybe let's just type it in. It might be faster.
All right. So I kept it at the original 3 clusters with the pixel value 1. I think in this case, Ken, the urban area is better reflected with the 1 value, just to confirm.
Yes, this looks nice, and it changes for cities which are near an ocean.
Okay, so in this, we'll test out the 2 clusters with pixel value of 1 being urban.
Hi, Ken.
Okay, so comparing with the ESA world cover, you can see these areas are some areas which are classified as urban, but they're not. But the accuracy is pretty okay for this. You can see here.
Yeah, but so when you look at Victoria,
Yes.
good. So when you look at the ESA one you're using to do the validation, you would see that that one gives a better reflection. But the darker areas, you see, move up a bit. Your cursor, move it up a bit.
Oh.
The dark. No, I mean on the image you were just showing.
Oh, okay.
Yes, this image on the left. Yes, where the cursor is. No, move to the left, please.
This left. My left? Okay.
Yes, so move a bit to the left again. Or the dark area in the center of the image. Yes, okay. That one. Yes, that is a forest reserve within Accra. It's called Achimota Forest Reserve. So you realize that what the K-means has done has basically taken off the entire area. And what you see in the right, the K-mean result, the predicted, that dark area you see there is the airport. And so ideally, yes, that's the Kotoka International Airport, the strip, the airstrip. You get it. So that basically should have given us something that looks like what do you call it? A bare surface or something like that, but it's same result as what you see in water, because what is on the bottom right is the ocean. Yeah. Meanwhile, you have very good accuracy results, you know, and so it will be useful to maybe look at how Kappa
Perhaps the case 3 will be better than the 1. Hello, can you hear me?
Sorry, I
Yes,
didn't
yeah.
catch the last part.
Instead of 1, perhaps we can choose the case 3.
Oh, okay. So we use 3 clusters and we take that the blue areas to be urban areas. Yes. Okay.
Yes, let's try the 3, please.
Me too, I think that is the number of cluster make this mistake. But if you try the 3 or the 4, you can have a nice result. Thank you.
So this is the result when we use the 3 clusters and we take that this value, the value 2 is what we think is the urban area class. Am I correct?
Yes.
Okay.
Yeah.
Yeah. So these are the results when we compare the 2.
Yeah, so Victoria, I see that this one comes a bit close to the ESA classification.
Yes. We can also run the metrics and see. So these are the accuracy metrics for this area.
So Victoria, just a small background is that in this scope, there is some cities without water which show good results. Then also some cities which are a little bit drier will show you better results, like something I did for Gulu in Uganda, which I could also show you from my side that I was getting Kappa statistics of around 90. So it means also the algorithm is going through various tweaks to adjust to the environment. And this from the side of optical has been an area of interest, like how do you map cities in very dry areas versus cities which experience good rainfall because of the reflectance. And in our studies, we've seen also cities with near lakes, the bare surfaces around the lake will also show like an urbanization. So it's quite a struggle to show the difference as we continue with the work. So it's not a very big defense. It's just a topic which is open for adjustments, and everyone is getting different results, and the algorithm is going through various tweaks. So what ESA has done is also not like 100%. It's just something that we can work with as we make adjustments. And we value the contribution of everybody in this call. So don't carry all the weight on your shoulders, Victoria.
Yeah, I mean, Ken, this is a very good start, basically. And I was just thinking when you were making your intervention that we could reduce the buffer and maybe exclude the ocean area and see what results we get.
That would be very possible. And also, if you may, Victoria, I could share what I was getting from this side as you work in the background.
Sure.
That we don't finish Victoria in one sitting. The crocodiles in these meetings are very dangerous. So just to put some humor in the meeting. So I did the same for Gulu in Uganda. It's quite a very semi-dry area. And there is also a little bit interesting. Could it because of the data available, or the algorithm was a little bit tweaking to that? So the city experienced some developments, and then there was a civil war around the year 2000. Then the city was rebuilding, and very much of it was comparing to what was on the world cover from the ESA. Even when I shared with the end user in Uganda, they were very interested in these accuracies, where Benjamin is looking with a strong lens. So it could be city by city case where we could do some various adjustments and tweaks. I was just trying to show you that. Then I did the same for another city in the same country, and the results were not so good. So it's a learning process from everybody. I even did for Kumasi, and the results were even worse. So I even didn't want to share them because that will mean that Benjamin will be very disappointed. So from what Victoria got from Nairobi, the results we agree were very visible with even what we have on the globe. So it's more of what our partners have done. So something around 79, 80 is fairly okay. But then we do for other cities, you really want to not even show the results. So it's more of a tweak and